Trying to search for features such as buildings or other features become fairly difficult without some way of locating ourselves. And likewise, graphic coordinate systems such as latitude and longitude tend to become very cumbersome to use, and so most mapping agencies have moved to a grid-based Cartesian system utilizing a series of X and Y coordinates to locate positions on a map. In Australia, one of the first metric map grid systems was introduced in 1966 and was called the Australian Map Grid of 66. It used the AGD66 datum. There were some errors in the AGD66 datum, and so in 1984 a new Australian map grid was developed and called the AMG84. The maximum difference between these two systems was only a few metres, so for most practical purposes they were identical. Most topographic maps that we use at present are based on either the AMG 66 or the AMG 84, although there has now been a move to a new map grid called the Australian Map Grid 1994, which uses the GDA 94 datum. Partly because of better modelling of the geoid through the use of GPS technology, and partly because of the push to make GPS seamless between countries. To do this, the world needed a single universal grid system rather than every country having its own system, such as our Australian map grid of 66. This new grid system, a further variation of the universal transverse Mercator projection, was called the World Geodetic System 1984, or as implemented in most GPS systems, WGS84. WGS84 has become the world standard for grid references and is the only common system accepted around the world apart from latitude and longitude. For this reason, a new Australian map grid system was adopted in 1994 based on the WGS84 world system and is called the Map Grid of Australia 94 and uses the GDA 94 datum. Satellite coordinates derived from a GPS using WGS84 or the world system will give essentially the same values as map coordinates based on our GDA 94 grid, and so effectively they're the same. Both geographic and grid-based coordinate systems are implemented in our GPS along with a range of other systems. So again, whenever you pick a GPS up for mapping exercises or fieldwork, it's important to check what system is set and change it to the appropriate system that you need. This is particularly important when adding to older data sets that may still be using the older coordinate system. Most new Australian maps are now being issued or updated or reissued, and they are typically based on the GDA 94 projection and datum. But this transition has been fairly slow, and many of the data sets incorporated in GIS systems, particularly throughout government, still use the older AGD66 system. So there's a little bit of a transition there, and we have to make adjustments for that transition. What we can see in our practicals is that grid lines on the new maps don't line up with grid lines on the old maps. To convert grid coordinates from the older Australian mapping grid of 66 or 84, the revised version of that, to our new mapping grid of 94 or GDA 94, we are required to add 130 metres to all the old eastings and 184 metres to all the old northings. Or likewise, if we were going the opposite way, we would have to subtract these values. So how does the Australian map grid work? Well, basically it was decided that the best map projection for Australia was still the universal transverse Mercator projection. Now this projection is one that has been designed to try and conserve area, shape and particularly direction for those countries that are located between the equator and mid-latitudes. It seems still to work fairly well at preserving any distortions in those areas. To minimise the distortion, the mathematical models were divided into thin strips, with the thin strips running north-south across the continent. So on the following slide of the Australian map grid, we can see that Australia occupies zones 47 through to 58, with the zone numbers increasing towards the east. The Australian map grid in fact covers a little bit more than the main part of Australia, because islands such as the Cocoa Islands and Norfolk Island come under the Australian Mapping Authority's jurisdiction, so it covers those islands as well. If we take a closer look at the east coast of Australia, we can see that here in Wagah we are placed in zone 55, and in fact if we refer to the topographic map of Wagah, we can see zone 55 indicated on the map. This is a usual convention for all topographic maps. We can also see that each zone is approximately equal to 6 degrees of longitude in width, and extends for the entire latitude of Australia. So when they first decided on the Australian map grid system, they needed some way of referencing the coordinates, and so many of the mapping authorities across the world decided on an origin, or a true origin for each zone would be the intersection of the equator with the central meridian, or the central line for each zone. Now, just to complicate things, and I've shown that in this particular slide, but just to complicate things, it was decided that this wouldn't work well for countries in the southern hemisphere, as we would end up with negative numbers. And so what they did was they shifted the true origin way down to the south, to what is known as the false origin. As we can see on this slide, what they did was shift the origin 500,000 meters west of the true origin and 10 million meters south of the true origin, somewhere almost down near the South Pole, and this position is called the false origin. This meant that we would have positive coordinates for each mapping zone in Australia, with all coordinates being east and north of that false origin. So let's take a look at this on the Wagah map and see how these coordinates are represented. So if we look at the Wagah map and go to the bottom left hand corner of the map, we can see various coordinates. The longitude and latitude of the corner of the map are indicated in degrees, minutes and seconds, but the ones we are interested in are located as meters north and east of the false origin. So if we go to the first grid line on the y-axis, or north, we can see a 7-digit coordinate in bold that reads 6,114,000 meters north of that false origin that we discussed earlier. Likewise, if we go across the map to the east, or the x-axis, we can see a coordinate in bold of 524,000 meters east of that false origin. You can also see some coordinates in light grey, and we don't need to worry about these as they relate to an integrated survey grid that is rarely used for mapping applications that we deal with. We need to understand the full reference, because our GPS typically reports to the nearest meter, so these full grid references are usually displayed on a GPS, and therefore this method is particularly useful in understanding how to locate ourselves on a topographic map. That said, it is very difficult to measure to the nearest meter on a topographic map, and therefore we have several abbreviated versions that I'll discuss shortly. Now, the intersection of these grid lines would yield a value that would read 524,000 meters east, 6,114,000 meters north, and I've indicated that intersection of those two grid lines by the orange arrow. So if we wanted to represent a coordinate for that, that's how we would represent that. Note, whenever you write a map reference, you always record the eastings first, followed by the northings. Also, the correct way to record the coordinates is to preface them with the map sheet name and number, although it isn't as critical here in this practical exercise because we know what map we are using. But if you were sending those coordinates out elsewhere, then this is a good habit to get into. Another convention when we break up the cell to get the final digits of the coordinates is that we never round up. Obviously, if the thing we were trying to locate was not on an intersection of lines, we would have to divide that grid square into sections to work out the final few digits of the coordinates, and I'll show you that shortly. In preparation for questions 8 through to 11 in your practical manual, let's look at how we might define some map references. A full grid map reference comprises of 13 figures. 6 are derived from the eastings and 7 from the northings. It's difficult to get down to a meter using a small scale map because we are measuring using a ruler, but we can probably have a go and get close to around 50 meters on a topographic paper map. Depending on the quality of our GPS, we can usually get to within 5 or 10 meters with most off-the-shelf systems, and down to a meter or even centimeters and millimeters with high-end systems while in the field. Here at the university, I use a GPS that's capable of centimeter accuracy. Alright, so a 4-figure map reference known as an area reference allows us to define the 1 kilometre grid square where an object might be located. The area reference defines the entire square grid, not just a point as indicated by the yellow box in the grid at the bottom of the slide. The 6-figure map reference gets us to within 100 meters of the location, whereas the full grid reference that I showed you earlier would get us to the nearest meter, but would require very careful measurement if we were trying to do it that way. We always define our references from the bottom left-hand corner of the grid cell when we're measuring with our ruler on our topographic map. As you can see on the map, the eastings are the vertical lines numbered from left to right on the map, while the northings are the horizontal lines numbered bottom to top. Note, while the easting reference isn't shown for the corner of the Wagah map, we can look at the sequence of the eastings and deduce that it must be 523,000 meters east, as I've indicated in green. Likewise, while the full reference isn't shown as we go across the map from left to right, we can see that the numbers 25, 26, etc. represent 525,000 meters east, 526,000 meters east, like I've also shown in green. Similar abbreviations are used for the northing, so you should get used to these conventions as they appear on all topographic maps. So if I wanted to give a full grid reference for the Crown Reserve indicated by the blue arrow on this map, I first need to determine its location doing the eastings first, followed by the northings. If I was to divide the total grid cell into 10 parts, I can see that the reserve is located about 9/10 of the way across the grid. The division of the 1 kilometre grid cell would look similar to what is shown on the lower right hand side diagram in this slide, except that we are trying to measure accurately enough to locate the feature inside that green box. Knowing the corner of the 1 kilometre grid cell is at 523,000 meters east, and knowing the reserve is roughly 900 meters further east, we can write the full easterly coordinate as 523,900 meters east. Likewise, for the northings, we can see that the Crown Reserve is roughly 250 meters north of the 6,114,000 north line. That's a bit of a mouthful. So the resulting coordinate would be 6,114,250 meters north. Please note, I'm doing this on the screen without measuring as an example, and if you wanted to do it and measure it accurately using a ruler, you might get a slightly more accurate value, but you should see how or the technique I'm using to determine the full grid reference is derived in this example anyway. The 6-figure reference simply drops some of the detail to give the corner of the small cell as indicated by the diagram in the lower right hand side of the slide. So we can see the large numbers in the grid coordinates, for example the 2,4 in the eastings and the 1,4 in the northing. These are the numbers that are used to identify the cell, with the third number derived again by dividing the cell into 10 parts. So for the Crown Reserve again indicated by that blue line, we know the corner of the cell would be 523,000 meters east, and if it was written there, the 2,3 would be in large numbers, and so we would write 239, with the 9 indicating it's 9/10 of the way across. Likewise, for the northing, we can see the large numbers in the full reference of 6,114,000 is 14. So these numbers form the first digits for the northing, with the third digit being 2. Note, I haven't rounded up in this case. In the full reference I use 250, but I'm not going to round that up to 3 because the convention says that we don't round up. The 6-figure map reference for that particular location would therefore read 239/142. You can typically drop the meters east and meters north if you want, although there's no real convention either way. The 4-figure reference simply indicates which 1 kilometre grid square the feature we are interested in is located, indicated by the yellow arrow. So again, we know we can use 2.3. The large number is derived from the 523,000 easterly reading, and 1.4 derived from the 6,114,000 northerly reading. So for this example, our references would read something like this. Full grid reference, you probably preface this with the Wagah map sheet and number prior to writing these down, but full grid reference would be 523,900 /6114250. The 6-figure reference would read something like 239/142, and the area reference would read 23/14. We tend not to, as I said earlier, write the meters east and meters north when we record these values, but there is no real convention, so you could do it if that helps make a little bit more sense. This should now allow you to find features and provide the locations in questions 8 through to 11 in the practical manual. If you're unsure, just go back through this practical a couple of times, or this explanation a couple of times, and you should become a bit more familiar with it.